Are we all set? Yeah, we're all set. Okay, well, I thought I would start this lecture with a bit of self-promotion. So I'm hiring two PhD students at the moment, basically. So if people are interested, then you can find out about it. Here, I've put the link into Discord already. So have a look at that or talk to me about it if you're interested in applying. Okay, but let's get rid of that for the moment and return to the lectures themselves. So as you might have noticed from the timetable, I'm trying to squeeze in an extra lecture. So what I'm going to talk about in this first lecture is the stuff that I should have talked about yesterday, but ran out of time for. And then there'll be this extra optional lecture over lunchtime. So if you want to come to that, feel free to bring coffee, sandwiches, whatever. Oh, a sandwich is not allowed? Okay, but coffee is okay. Definitely don't bring sandwiches then. Anyway, moving on. So at the end of yesterday's lecture, I got to the point where I'd kind of defined a GPT, but I'd never really explicitly written down the definition of a GPT. So I thought a good place to start off would be to write that definition. So GPT is a process theory. In particular, it's one of these process theories where we've quotiented away the context information, leaving only the equivalence classes. But it's not just some sort of arbitrarily, some arbitrary quotiented process theory. It's one where the theory that you start with has a particular structure. So it's where G has all So it's one where G has all possible classically controlled processes and where all effects for a system and where all of the effects for a given system differ only by context. So that when we go to the quotiented theory, we're in one of these causal theories where we've only got the unique way to discard a system. Some of you might have seen other approaches to GPTs where there's lots of effects. We'll get there in a bit. So if you're a bit concerned about this idea that there's only one effect, we'll try and resolve that confusion as we go today. Okay, so this is my definition of a GPT. And today what we're going to do is try and look at what the consequences of this definition are, try and get a bit of more of a sort of concrete representation of things that you might hope to start going and doing calculations with, rather than this more abstract definition. Before that, though, I want to go back and talk about no signaling a little bit. So this ties in very closely with the stuff that Paul was talking about yesterday. And it goes to something that I skipped in the first lecture, which was the idea that if we have one of these causal process theories with a unique unique effect for every system, then it's necessarily compatible in a certain sense with sort of relativity theory and sort of space-time causal structure. So let me switch over to the slides for this. How do I go full screen? There we go. So the idea is, imagine we're trying to now sort of think that we've got our systems in space-time, and we want to describe this sort of Bell scenario that we saw yesterday. Well, diagrammatically, we draw it something like this. Where's my pointer? over here. So we imagine that we've got Alice sitting over here in sort of one space-time region, and Bob sitting over here in some other space-time region. But in the sort of past intersection of their light cones, there's some sort of common past that happens. So they've got some shared state in the process theory. And at the moment, this could be a GPT as well. So it could be the case that these were sort of classical inputs and outputs, labeling, as Paul had, they were sort of classical inputs and classical outputs, the inputs representing the measurement choice and the output representing the outcome of the measurement. But we can sort of be slightly more general than that and just think of these as being some sort of input system that Alice has and some sort of output system that she has. We don't need to commit to them being classical. But, okay, so this is like the global picture of what's going on in this sort of Bell scenario. But let's say we want to look at things from Alice's perspective. What does Alice see when she's doing experiments? Well, she sees something like this. She doesn't have any access to what Bob's doing because he's sort of space-like separated. So from Alice's perspective, she just ignores what's going on Bob's side. So she discards this B system. Well, she doesn't physically discard it, she just doesn't have access to it, so she ignores it. And now we're just going to use the properties that we demand that this discarding has. So this discarding, we've said, satisfies a bunch of equations, and I put them all up on one slide, and I'll try and walk you through it slowly. So this is Alice's description of the Bell scenario. And Bob is doing something in his lab, this process B, but this is a discard preserving process, because we're assuming that all processes are discard preserving. So this discard here, it just falls through to the input systems. So we get to this description over here. But we also know that discarding some composite system, in this case this sort of SB-Y composite system, discarding them together is the same as discarding them as two sort of individual discard processes. And then we can do a bit of just like basic diagrammatic manipulation and see that this is the description that Alice has of the physical scenario. And you'll notice that Bob's input, this Y system here, is totally disconnected from everything going on Alice's side. So there's nothing between them at all. So whatever Bob does to this system Y, he might prepare it in some state or transform it in some sense. Whatever he does here, it can't have any impact on what Alice sees. So this is like the description of Alice's local physics. So this is like a very sort of strong version of no signaling. We have this diagrammatic disconnection between them. And in the special case where we have sort of X, Y, A, and B as classical systems, then this reduces exactly to the definition of no signaling that Paul gave in his lecture yesterday. Okay, so that was one little bit that I wanted to cover. So this is why this thing is called a causal process theory, basically. It's because we end up in a situation where in order to send signals, we have to send some physical system. And we imagine that the sending of physical systems obeys the causal structure of relativity, hence causal process theory. Yeah, this question.
Does this idea still work if I include time? So otherwise, Alice could just wait until she can, in fact, get the signal that Bob has, right?
Yeah, so you could imagine that, yes, if you waited sort of longer and described the physics at a much later time in the universe, then there would be some sort of common intersections to the future light cones, and you could get Alice and Bob coming back together and discussing things. And then at that stage, Alice should no longer be ignoring Bob's system. If she says, I'm going to ignore Bob's system, but she has access to it, then this is sort of just a misuse of the formalism. Okay, so yeah, that was filling in one gap. Now, the next thing I wanted to talk about was sort of the convex geometry and trying to get a more sort of concrete geometric picture of what's going on. Because we've sort of said abstractly that the sets of processes form convex sets, but it's nice to be able to give these sort of a representation. So the idea is that if we look at the set of states for system A, we're going to call this capital omega A, and this is the set of states I need to remember my conventions. That should be a red system, I think. Then we've argued abstractly that this thing is a convex set. But kind of what sort of convex set can it be? Can it be an arbitrary convex set, or does it have to have some structure? So rather than talking about sort of general systems, let's start off by looking at what classical systems look like, because we understand those well. So in particular, let's look at omega sub x, which are the set of things like this. So this is the set of classical probability distributions. And it's sort of well known that any probability distribution can be uniquely decomposed in terms of delta function distributions. So what this means is that geometrically, this object is a simplex. So if x is just, say, a singleton set, then this is a single point. If x is some sort of two-element set, then the geometry is a line segment, sorry. So you've got sort of the two endpoints of the delta functions, and then everything else is given by some probability. If we go to a... Okay, sure. If we go to a three-element set, then we end up with a triangle. And if we go to the four-element set, we get a tetrahedron. And if we go to a five-element set, then I can't draw it anymore, so let's just stop where we are here. So these are the classical probability distributions. Then if we say, okay, so those are the probability distributions, what about sort of the other classical stuff we can do? Well, we've got stochastic maps, and we can characterize their convex geometry as well. But we're not going to go into the details of that, because what I want to turn to instead are sort of effects other than the discarding effect. So we've talked about the discarding effect a lot already, and we've seen that in stock, this is just marginalization over probability distributions. But it's also very convenient to try to not just talk about measurements where we keep track of all of the different possible outcomes, but where we just focus in on a single specific outcome and try and look at what's the probability that that particular outcome occurs. And we can sort of do that in some sense, that we can say, well, we've got some probability distribution, we've got some measurement, the outcome set might be y, and this thing we've said is just some probability distribution over y, and then if I give you a probability distribution written down in some concrete notation, then I can just read out the probabilities of the different outcomes for that. I mean, this is something like py1 dot pyn, for example. And I can just say, well, this thing is what this object is describing. Sorry, these should be like Q's or something. And so if I want to know the probability of getting outcome y1, well, it's sitting here in my sort of notation. But it's very useful also to try and directly encode this kind of stuff into the diagrams themselves. So to have something where essentially what we want to get to is where we can write these probabilities here as scalars in the theory. So to do that, though, we have to introduce a new diagrammatic element. And this is going to change the geometry in a very precise but interesting way that we'll get to shortly. So the idea is that we're going to have a new kind of process, which we're going to label like this. And in the lecture notes, I drew these as black triangles with white text inside. I can't really do that on a blackboard, so I'm going to draw these as green triangles with green text inside. Is this color obviously distinct from the white?
The color is more obvious than what's written there.
Okay, so yeah, let me try and draw it bigger. So this is a little y, and this is a big Y. And so this is my diagrammatic notation that is sort of supposed to be looking at a particular probability. So in particular, the idea is that if I have some probability distribution over y, some q probability distribution over y, then this thing should be equal to q of little y.
Can you try blue instead of green?
I can. Is that better? I mean, now it's a mess, but even more of a mess, I should say. Okay, so this is a new diagrammatic element that I'm going to introduce to my theory. And the problem is that we're trying to define a process theory here still. So I can't just sort of add a single element and hope for the best. I've got to figure out what the consequences of adding this extra bit of notation are for the theory as a whole. So in particular, we've seen things like that, well, we introduced this new element, and now I've got scalars other than 1. Yeah.
In the last lecture, we had that all effects are operationally equivalent.
Yeah.
Like in GPPs. So this should be operationally equivalent to describing something?
No, so this is a new effect that is not operationally equivalent. That's a good thing to point out, yeah.
This wasn't in the GPP.
Exactly, so I'm now adding new stuff, which is why I'm drawing in a different color to make it obvious that this is a new thing that's being added. It wasn't part of the basic definition that I gave yesterday. This is like a new mathematical tool that I'm adding to the theory, and I'm going to explore what the consequences of adding this new mathematical tool are. So now this is some element of the unit interval. I think it's quite easy to see that you can get any element of the unit interval by appropriately picking q. So then this is no longer a causal process theory. We've got lots of different effects that are operationally inequivalent to one another. And so now, well, I've got these scalars around, so one thing I can do with them is I can compose them with states. So now I can draw states. I'm just going to call this S for scalar. So we have things that are like some scalar now S, which is any value in the unit interval, times some probability distribution P. And so then this thing now is no longer a probability distribution. This is a thing called a sub-normalized probability distribution, because if we sum up the different values, it will sum up to S, which in general is going to be less than 1. Was there a question? No, okay. So we get this new kind of state, these sub-normalized states. So we can then look back at our geometric picture and see what this does to the geometry. And basically it takes these convex sets and it embeds them inside a vector space that's one-dimensional higher, and then it allows you to take convex combinations with the 0. So let me draw an example of that using the 3-element set. So essentially what this does is, this is an object that lives in 2D, it just lives in the plane, but we're going to embed it into 3D, and in particular we can pick a representation such that the vertices of the triangle go to the basis vectors. So this now is my triangle. This is the origin, the 0 vector. And now we get all of these sub-normalized probability distributions lie sort of underneath the between the triangle and the 0. So it's sort of this 3D space now. Which turns out to, okay, geometrically this is actually another simplex, but it's not the same as this simplex. This is the simplex of probability distributions over some 4-element set, whereas this is a simplex of sub-normalized probability distributions over a 3-element set. So it's important to, even though they might look the same, they're quite different mathematical objects. We can also think, okay, we've introduced this particular kind of new effect, but now I've added this new effect, I can use it to construct more new effects. So in particular, if I have some stochastic map S from X to Y, and I compose this with this new effect little y, then this defines a new set of objects, and these are known as response functions in the literature. So these are response functions for the system X. Concretely, what you can think of these as are sort of 0, 1 valued vectors. So if we look at what they look like in this kind of picture, we get something like this sort of cube shape, where this is, again, the 0. Up here, we have the discarding effect. And then these points here would be, say, x1, x2, and x3. And then we get a bunch of other things as well, which are sort of coarse gradings and convex combinations of these particular effects. So if we looked at the geometry in the original GPT, we would have had a single effect, which is the discarding effect. But as soon as we start trying to add in this new mathematical object that lets us look at particular outcomes, then the effect space becomes a much more interesting geometric structure. And this is the kind of perspective that you'll see a lot in the GPT literature, which is why I'm talking about it today. And similarly, you get extensions of the geometry of the transformations as well, which I'll not go into because it's complicated, essentially. Okay, now this was all for just extending stock. So we have a name for this process theory, which is stock, plus everything you can generate with this new effect, and that is called substock. So we get this new process theory, which includes not just stochastic processes, but substochastic processes that happen with sort of probability less than 1. And I think it's not hard to see that this is sort of a super theory of stock. It was just sort of defined as an extension of it. But if we sort of extend stock to substock and then go through this sort of process of constructing a GPT, then it's not just the stochastic part of the theory that picks up new processes, but it's the GPT as a whole. So in our GPT, we started talking about this space of states for some system A. And generically, you can get sort of any bounded convex set of states as the state space for some GPT. So you can get things that are sort of polytopes, so it could be a square. You can get circles. You can get high-dimensional things that I can't really draw. You can get sort of, that's not convex, funny sort of asymmetric shapes and so on. It's pretty much anything you want. The key criteria is what I briefly said, which is that this should be bounded. So there should be no direction where you can go off to infinity. in these shapes. And the basic reason for that comes down to this quotienting that we did. Essentially, if we had some direction that you could go off to infinity in, then I won't go through the details that's in the lecture notes, but basically in that direction, you have no measurement that can distinguish the states that are varying only in that direction. Because sort of if you did have such a measurement, and then you sort of go far enough along in that direction, eventually you would start getting probabilities for outcomes that were either less than 0 or greater than 1. So because we can't have those kind of probabilities, you can't distinguish states that vary in that direction. So you have to have these sort of nice bounded state spaces. So these are kind of examples of omega A. And then when we extend stock to substock, then very similarly to what happened over here, we end up extending these convex sets by embedding them inside a bigger dimensional vector space and taking convex combinations with the origin. So we get a bunch of sub-normalized states as well. So to give one example of that, if the state space was a circle to start with, then we embed that inside a vector space one dimension higher. So this is now like a 3D ice cream cone kind of shape. So we have omega, draw that bigger. We have omega A here, and then we get everything else here, which we could call omega A sub for sub-normalized, for example. Okay, and like we extended the effect space in stock from just a single effect to this big sort of cube or hypercube generally of effects. Similarly, when we look at the GPT, we're going to go from just a single deterministic effect, which I'll draw here, to some geometry that contains a lot more.
By raising dimension by 1, you mean adding 1 vertex, right?
Yeah, so we had this sort of 2D convex set. I embed it into 3D, and I take the origin, and then I take convex combinations between the convex set and the origin. Yeah, so this is supposed to be a 3D picture. Okay, so the effect space originally was just a single point, but now we extend it and we get the space of things that look like the following. So we have some measurement process of system A, and this might have outcome Y, and then we compose that with this new effect that I added into the classical part of the theory. And if we look at the space of these objects, then we get quite an interesting geometry coming out. So I'll try and build up to it. So for simplicity, I'm going to imagine that I'm just going to look at 2 binary outcome measurements here. So Y is just a 0, 1 valued set, and we're just going to consider the effects that we get using 2 different measurements. So I can always compose M with sort of the 0 effect. So I get sort of an origin. And then if I compose M with Y equals 0, say, then I'll get some point. And if I compose with Y equals 1, I'll get some other point. So I end up, for the first measurement, getting this sort of square of effects. And then if I consider my second measurement, then I get another square. It's not a totally independent square. It's a square that also has to be sort of joined at the 0, because 0 times anything is 0, so it doesn't matter which measurement I talk about. And we know that they're going to have the same discarding effect as well. So we get another square that's sort of glued at these 2 points. But in principle, it could be in some other plane. It doesn't have to be lying in the same plane, so we could be imagining something in 3D or in some high-dimensional space. So I'm going to attempt to draw a 3D diagram. I practiced this, so it should work. Let's see. There we go. So, sort of. So this is supposed to be some square that now is lying in some other plane, like going into the board. So by considering these two measurements and the sort of different effects, classical response functions that I can compose them with, then for one measurement I get this square, for the other measurement I get this square. But I can also use the standard GPT stuff and take convex combinations of these. So if I take convex combinations of these, then I end up getting this kind of geometry. So in this example, it turns out to be an octahedron of effects. More generally, what you get is discussed in the notes, but basically for each measurement, you get a thing called a zonotope, which is a bunch of vectors and then all linear combinations of those where the linear coefficients are valued in 0, 1. So for each measurement, you get one of these zonotopes that are glued together at the origin and the discard, and then you take the convex hull of all of these things. As I said, the details are in the notes, but this is kind of the rough picture to have in mind. You have these sort of shapes that are glued together, and then you take the convex hull of those. Okay, how am I doing for time? 10 minutes? Okay. Great. And so very often, okay, so then let me give some notation. So if I vary over all possible measurements and all possible y's here, then in the GPT literature, this is very often denoted as sort of a big calligraphic E sub A. And this is what people often think of as the effect space. So it's the effects, including those that you get by adding in these sort of substochastic processes as well. And so commonly you'll see things like definitions along the lines of a GPT is sort of omega E and some sort of inner product. So you'll commonly see this kind of definition in the literature. And the idea of the inner product is that you use the inner product to take a vector in this space and a vector in this space, take that inner product, and that gives you the probability of seeing that particular effect given that particular state. From my perspective, this is just like a very small part of what a GPT is. Basically, it's just the characterization of the states and the effects for a single system, and it's missing all of the sort of compositional, all the structure, all of the sort of transformations, and so on. But this is just a warning that this sort of definition will pop up in the literature a lot. Okay, so I think I've talked quite generically or generally so far. I think it's about time I actually told you how quantum theory looks in this language. So, finally, quantum theory. I think maybe from some of the geometric picture, things are not too hard to understand, so I'm going to start there and then try to work in the last few minutes to sort of the general statement of quantum theory in this language. But at least for a qubit, I hope that some of the pictures I've been drawing are not sort of a million miles away from what you're familiar with already. So for qubits, hopefully you've all seen this sort of block sphere representation of things. So we could call this sort of omega qubit. So this is the convex set of normalized states for a qubit system. So this is our omega, but we've seen that it's often useful to use these sort of sub-normalized states as well, and the procedure is exactly the same. It's now unfortunately a four-dimensional space, but we go into some four-dimensional space, and then we take combinations with the origin. So let me draw that in blue to try and be consistent. And what sometimes confuses people a bit with this kind of representation is that now we're representing quantum states by real vectors. And this isn't just some sort of quirk of the qubit, this is totally generic to quantum systems. Basically, you just need to notice that density matrices are all Hermitian operators, and Hermitian operators define a real vector space. Because if we take any sort of complex combinations, then we end up with things that aren't Hermitian anymore. So this is now a diagram in the space of Hermitian operators on a two-dimensional Hilbert space. So this is the states. And then the effects, I'm not going to try and draw a 4D diagram again. I'm going to take sort of a 2D slice, a 3D slice through the space of effects. So in particular, I get the zero. I get the unit effect, the discarding effect, and then I get this sort of circle of the points on the boundary of this circle are rank 1 projectors, and then I get this sort of double cone sort of picture going on. So to try and tie this back to the picture I was drawing up there, yeah, there's a question? On this picture? Yes. So like we have 0 here, 1 here, plus, minus.
And then it's the sub-normalized. Okay.
Yeah, so then I'm taking this 3D sphere, I'm embedding it in 4D, and then this is sort of the fourth dimension going, I don't know, out of the board or something. That's why I chose to do this 2D slice here. So as a 2D slice, we could imagine that this is like the 0 projector there at the back, the 1 projector there, this one can be plus, this one's minus, and then I get the 0 vector, and then I get the unit, which in this notation is just the identity Hermitian operator. So this is my effect space. So this is calligraphic E for the qubit. And then the usual way that we compute probabilities is by doing sort of trace mk rho, where mk is some vector in this space, rho is some vector in this space, and the trace is turns out to be an inner product on the space of Hermitian operators, the Hilbert-Schmidt inner product. So we can see that this is very much mirroring the kind of structure that we wrote up here. Often you'll also see people not talking about effects as being vectors and then computing probabilities with the inner product. But people will talk about effects as being linear functionals on the space of states. And these two pictures are totally equivalent to one another thanks to a theorem called the Ryers representation theorem, which basically says that whenever you have a linear functional, you can always think of it as a vector and using the inner product, any sort of arbitrary inner product that you choose. So that's the geometric picture for the qubit, and it all generalizes to sort of arbitrary dimensional, well, arbitrary finite dimensional quantum systems. Okay, so that's quantum theory geometric perspective. What about quantum theory as a process theory? So here we have our systems. Systems in the process theory are going to be labeled by the spaces of Hermitian operators on some Hilbert space, finite dimensional Hilbert space H. And then, so these are our systems. And our processes. Our processes are then just CPTP maps. And then we get that parallel composition of processes is just the tensor product. And sequential composition is just composition of CPTP maps in the usual sense. And then you can sort of build up arbitrary diagrams, as I mentioned in the first lecture, using these two kinds of composition. One thing to note is that I've talked about these as CPTP maps, and this trace preservation condition is exactly the discard preservation condition that we've talked about a lot. So when I say that composition is, that processes are CPTP maps, this means that we're talking about the causal process theory, i.e. this kind of GPT that we started with. But we saw that it was nice to extend things and deal with sort of sub-normalized things as well. So we can also define the sub-normalized theory, and this is basically going from CPTP maps to CPTNI maps. So these are completely positive, trace non-increasing maps. And that's basically it. This is sort of quite a compressed definition. Unpacking how this works takes a little bit of effort. In particular, to understand how this definition covers states is slightly weird. Because in this formalism, you think of quantum states as being a special kind of CPTP map. They're CPTP maps where the input is some trivial system. So if you take the one-dimensional Hilbert space and the space of Hermitian operators on the one-dimensional Hilbert space and look at the space of CPTP maps from that to some other Hilbert space, then it turns out that this is the same thing as a density matrix. This is kind of subtle to work through, and I don't have time to go through all of that now. But you can also just say that things like this are density matrices, and that the discarding is the partial trace. And then the sub-normalized effects are POVM elements. So things like this. So that when I compose one of these with some state, then I get the probability by using the standard trace, the Born rule, basically. But as I say, this stuff at the end, in theory, can be derived from the definition that I gave. You can also just think of it as additional specification. Okay, so I'm going to finish there and say that in the next lecture, the thing that I haven't talked about here so far with defining the quantum theory is I've not talked about how it interacts with stochastic stuff at all. So in the lunch lecture, I'm going to talk about how we can see the structure of stock as being emergent from quantum theory. Okay, are there any questions?
So up in the definition, the general definition of a GPT, you wrote just omega and E, right?
Yeah.
And usually we write omega qubit or omega A or something. So, but what type of prescription are omega and E?
So this is, I shouldn't have probably written that down. This is supposed to be just the kind of thing that you might see in the literature, where people often just focus on a single system. They don't care about composition. They don't care about looking at other systems. And then you just give a particular omega some convex set and some particular E, which is the effect space. Yeah, so then a GPT would just be like a qubit, for example, rather than quantum theory as a whole. But I think a better thing to have written there would have been like something along the lines of, to every system in a GPT, I can associate this triple, some omega A, some EA, and some inner product. So that's how I think about it. This is sort of data that you can extract from the full GPT and use it to characterize, to some extent, characterize a particular system within the GPT.